Welcome back, Physics 30. This is section FI2.5, electric currents produce magnetic fields. So here we'll represent the direction of the magnetic field produced both by a long straight current carrying wire or a current carrying loop. Use the right-hand rule to determine the direction of the magnetic field produced in a long straight current carrying wire and a current loop. So during the 18th century, many scientists sought to find a connection between electricity and magnetism. A stationary electric charge and a magnet were shown to have no influence on each other. So charging something using static electricity and magnets, nothing. But in 1820, Hans Christian Ørsted found that when a compass is placed near a wire, the compass needle deflects if and only if there was an electric current going through that wire. Just like over here. So here we have a wire kind of coming out of the page three-dimensionally. If there was no current going through it, these compasses would just point towards the magnetic, the North Pole of the Earth. But once you have the current going, you can see they all point in a circle shape around that wire. So Ørsted's experiment showed that an electric current must produce a magnetic field, which is affecting these compasses around that wire. He found a connection between electricity and magnetism. A compass needle placed near a straight section of a current-carrying wire experiences a force, causing the needle to align tangent to the circle. So if you imagine this is a circle, each compass needle is tangent, hitting that circle at one point only, just like that. Causing the needle to so tangent to the circle. Thus, the magnetic field lines produced by a current in a straight wire are in the form of circles, with the wire at its center, as seen below. So if you were to sprinkle iron filings around, we would see circles around there because they're lining up. They're becoming mini compasses themselves. If you look at this piece of wire here, you can see that if it's going up, you have these kind of three-dimensional circles coming out of the page, going into the page. The direction of these lines is indicated by the north pole of the compass in the above figure. There's a simple way to determine the direction of the magnetic field lines in either case, and it's known as the right-hand rule. And the right-hand rule is to grasp the wire with your right hand so that your thumb points in the direction of conventional current. Now, we need to stop there because conventional current is thought of as being the movement of positive charges. So if you were to imagine a battery, to say it's a car battery, positive, positive, negative, negative, and if we were to join these up, this would be conventional current. So going from positive to negative. So that's conventional current. Conventional current. Of course, there's another kind of current, which is the true way of looking at it. Positive charges flowing one way is the same as negative charges flowing the opposite way. Electron current. Okay, so we'll kind of look at this in two ways. We'll look at it in terms of conventional current and electron current. So if you see a capital I, usually in a picture or a textbook of physics, that usually indicates conventional current. Think of it as the flow of positive charges. Unless it's otherwise stated, if you see a picture of a battery, you can be able to tell if it's electron or positive. So the thumb points in the direction of current, and then your fingers will encircle the wire in the direction of the magnetic field. And we use B as the symbol for magnetic field. So if this pen was the wire carrying current this way, and let's say it's positive, so my thumb points in that direction, and my fingers encircle in such a way that you can see it's a circle. So this is a circle going around. So you can see it matches this diagram. This finger here is this arrow here. So the magnetic field will be going to your right on the near side of the pen and to the left on the opposite side of the pen. So it's a circle around the wire. Now, positive current would flow in this direction. Negative current, of course, flows in the opposite direction, so I would use a left-hand rule. So I'd grab it the opposite way with my thumb pointing down, and it's kind of hard to see, my hands are too big. I get identical scenarios here. Conventional current, electron current, my fingers are going to go around the same way no matter what. Okay? Magnetic field lines due to a circular loop of a current carrying wire can be determined in the same way. So if I have a loop here, have your thumb and then grab around that loop, and you would get the same result there. Kind of easier to see this loop here. If current is flowing in this loop going this way, so your thumb here is pointing that way, and we could see the circles that are forming here. Kind of hard to draw, but you would see that it's forming circles like that. Unlike uniform fields as seen earlier, the magnetic fields shown around a current carrying wire are not uniform. Fields are different in magnitude and direction at different locations. All right, so right-hand rule. If it's conventional current, your right-hand thumb points in the direction of the current, and then your fingers will mimic what the magnetic field line looks like. If we think of current as the flow of negative charges, use your left hand and your left thumb points in the direction of electron current. Okay, so that's it. A very short section. Just kind of wrap your head around that rule there and see if you can complete the diagrams on the paper for FI 2.5. All right, we'll see you again.